OSPF. Now, there are many routing protocols available for our use in our networks. The key is finding which routing protocol best meets the needs of our specific network. Now, there are things out there that are designed to help us out, and the most common tool we can use is the categorization of those routing protocols. They can be categorized by protocol in some instance, and what I mean by that is you're going to have a specific set of routing protocols available for you within the TCP/IP environment. You have another set of routing protocols in a Novell network environment, another set within the IBM protocols, and on down the line. So that's one way of categorizing it. Another is whether it falls into one of two camps, being IGP or EGP. IGP being the internal gateway protocol, EGP is external, and you have that line of demarcation and the function of those routing protocols. But the most common use of identification is whether they fit into one of three categories. The first one being distance vector, the second link state, and the third a hybrid of both of those together. So in this nugget, we're going to learn about the most commonly used link state protocol, and that's OSPF. We're going to start out by looking at or learning about the different types of terms that we're going to have, and it's going to form that basis or that stage for our further discussions. After that, we're going to take a look at the process involved, how OSPF works. Following that, we're going to look at the various tables that are used within OSPF, because when we talked about some of the other routing protocols we've used, we really talked about having a route table and that's it. Well, we're going to have an interjection of a couple of other tables, and we're going to talk about that in this section. And then we're going to end up talking about configuration commands. All right, let's start as promised with our terms. First term you're going to see there is a neighbor, okay? Now what we're talking about within a neighbor, so I have to have one router involved for sure, and in this instance you kind of get the idea that I need another one, right? And I'm going to draw a little cloud here, and it's going to represent our subnet, okay? Not a whole local area network that's going to be comprised of many subnets, but just one subnet, and these two routers are going to be on that same subnet, that same address space, right? Well, what you're going to do is you're going to have these individuals send out some information, and the information they send out is called a hello packet. And this is if they are OSPF enabled, okay? This one's going to send it. This one's going to send it as well, and they're going to identify themselves as being neighbors by exchanging that information. And there's actually, and we're going to talk about this in more depth, a table that they're going to populate based on that information. But staying with the process here in this term, a neighbor is simply two routers that are neighbors together that are directly connected, and they participate in the same routing protocol. In this instance, OSPF. And OSPF identifies them by exchanging these hello packets. All right, beyond there, we have the idea of adjacencies. And these terms, specifically these first two, are going to build on each other. We have this idea of a neighbor, so we have two routers, right? And they're going to consider themselves neighbors, put themselves on their table, and now they want to be considered adjacencies. What they're going to do there is they're going to go ahead and wait until they have the same topology table. Now here's another table, and I make mention of them here, but don't spend a lot of time thinking about them as of yet, because you know I'm going to define them for you later within this nugget. But once this router and this router over here have the same topology table, which, to give you a brief definition here, is a snapshot, if you will, of how the entire network looks. It's not a routing table, because remember, routing tables are populated with a best path on how to get from one point to another, right? Well, what I'm saying here is this is a snapshot. This is going to show me all paths throughout my network, just a whole big picture. Well, once these two snapshots match on these two routers, then they're said to be adjacent or formed an adjacency. The other term we want to talk about right now is a designated router. The designated router has certain responsibilities, but first we're going to define exactly what it is. It's a central router. And being the central router, it's going to have to form adjacencies, we just talked about those, with every other router within a specific area that participates in this OSPF protocol. So here we go. Let's say that I have one here, and I'm going to draw my subnet again. The cloud's starting to look like a circle, isn't it? Oh, here we go. And on that subnet, I'm going to have 4 different routers. All right, I'm going to say that one of them, in this case, this one here, is going to serve as a designated router. So there has to be adjacencies from here to here, from here to the second, and from here to the third router. Now, I don't want to trip you up. I've mentioned a couple times here the word area. What do I mean by area? Just a specific amount of space, right? Well, you know that we're normally talking logical and not physical space as far as demarcation points when we talk about networks, right? So here I'm going to define an area in short for you, because we're going to define it further later on within this nugget. So basically, we're saying it's a group of routers that share the same area ID. So you know there's a form of identification, and it has to do specifically with OSPF. So we're going to say, yeah, I'm in an area, I'm in an area, I'm in an area, I'm in an area. Let's say that they're all in area 0 here. And you're going to get used to seeing area 0. We're just saying we all want to play in the same small little community. And then as we were saying before, we're going to have a designated router. We've identified kind of the requirement of what makes this router a designated router. But now let's talk about the responsibility here. It's going to have the responsibility of maintaining that topology database that we talked about earlier throughout the area. So it has to be up to speed on this database, and because it forms these adjacencies, it's going to make sure that it gives that information and shares that information with every other router within that specific area, right? All right, let's talk about the way that a designated router is going to be chosen, I guess, right? There's two methods. One is going to be an automatic method, and you can kind of just let that run. Each of these routers is going to have IP addresses on different interfaces, right? I mean, that's a given. What they're going to do is they're going to look at the IP addresses on this router, and they're going to take the highest one with the highest value, and they're going to say that is going to be your ID. They're going to do that to every one of these routers, and then there's going to be a comparison of these IDs, and whoever has that highest IP address, understand that in this case, highest is better, is going to be labeled as a designated router. Well, in this case, if there were different types of routers, let's say that this is a high-end router, and then we've got some low-end routers out here, we really want this one to be the designated router, right? Well, we can't control that as well when we're just talking about IP addresses, but we can when we use a specific command. And that command is going to allow us to designate exactly which router here we want to perform as a designated router. Without further ado, here's the command. It's IP space ospf space priority, and then what we're going to provide is a number in reference to that priority. Now the range of the numbers is between 0 and 255, and as we said before, the higher priority is the better. Now here's the key. As soon as you put a priority on an interface within one of these routers, let's say you provide it right here on this interface that's connecting out here to this subnet, then it is going to go ahead and win that designated router election, and there you go. You've pointed yourself at what router you want it to be, and you've made that happen. All right, next thing we're going to talk about is link state advertisements. And the reason is you're kind of following the flow here of first we have just two routers on the subnet, and we're understanding how they first discover each other, right, within this process, and they form a neighborship. After that, they're going to come together and share a topology table, and then they'll be called an adjacency. Beyond there, we've identified the idea of an area, as you see it here. All of these routers, same routing protocol, same area, OSPF, area 0, and they communicate with each other. Within that area, we've assigned a designated router responsible to form adjacencies with every other router in that area and then to maintain that topology map. Now we're going to talk about link state advertisements, because here we're talking about how these different devices are going to communicate with each other, their specific structure. As with anything, when we talk about a protocol, we're simply saying a specific way in which different devices are going to talk to each other. Well, here we go. Link state advertisements are packets, so we're going to list them as such. They're going to be packets that are going to list different router links. Here, let me give you one individual router. It's going to list all the links within there, and it's going to talk about the state. So you get the idea, link state advertisement, right? And by state, we're simply talking about the status of that specific link, and the link is going to be between two different routers here, and we saw that within the beginning. And then we have the idea of updates. Link state advertisements were new probably to you, specific to OSPF, because this is our first link state protocol that we're going in depth with. And now we're going to talk about updates. Well, when we talk about distance vector routing protocols, remember I mentioned that in the intro of the categories. I had distance vector, link state, and then the hybrid. When I talk about distance vector routing protocols, we're usually talking about a periodic update. What does that mean? That means that I have a router here, and it's going to send out information concerning routes to other devices, in this case another router, every period of time, a specific period of time. It may be 60 seconds, it may be 90 seconds, it may be 30 seconds, whatever it may be, dependent on the protocol. Well, here we're talking about link state, and they're going to introduce a new idea, and it's called incremental update. Simply it's saying this, that we're going to update from one router to another anytime we see a change. And the idea is that if we don't see that change, we're not going to update. But you understand that you could go a long length of time then with no updates, right? And it might cause concern within your network. So what's going to happen is they're kind of mixing this up. They're saying incrementally, we're going to say that every time there's a change in the network, this router here is notified of a change, it has to update all the other routers within that network saying, hey, there's a change that has taken place to start that idea of convergence. So they all have that same topology database or topology table again, right? Well, here's the thing. There's also a catch-all. Within this periodic update, they're saying that if 30 minutes, not 30 seconds, understand we're talking about 30 minutes, if 30 minutes pass and we haven't had any update at all, go ahead and send a periodic between these devices, changing information as far as what the tables look like to make sure they're on the same page. So that's the catch-all for us, right? The safety device. So you have within OSPF the idea of incremental and periodic updates. All right, that's going to do it for terms. Now what we're going to do is we're going to move into a section to talk about that process. And we kind of already did, so we can run through this a little bit faster. When we talked about that neighborship, and this is kind of a Valdezism. I don't think you're going to see this in too many books. But, you know, we have relationships, right? And that's what we're setting up between these two devices, relationships to be neighbors, so neighborship. Anyway, if you like it, stay with it. If you don't, just call them neighbors. Well, here we go. We talked about the hello packets. They were going to be transferred between these two devices, saying, hey, yeah, we're neighbors. Let's list ourselves on a table. Then with the adjacencies, making sure that the topo table, the topology table, matches on each one. And then we've gone through our election process. So at this point, we have an area populated with a lot of routers, and it seems like, you know what, we got things going pretty well here. We have adjacencies built in. We know that each router has the same topology table. We know that they have neighbor tables listing each other. We're doing pretty good, right? We haven't gotten to the point of establishing the routing table as of yet, but sounds like something we should get into at this point, doesn't it? Well, let's go ahead and do that. Going into the different tables, we've talked about having a neighbor table. So if I'm router A, list that out here, and then I have router B out here, I have router C, and I have router D, again, in that same subnet, sharing a piece of real estate, if you will. And what I'm going to do is on router A, it's going to list router B here, router C, and router D, and the information that it took to establish that neighborship, right? Then in our topology table is going to be a snapshot, as we mentioned earlier, of the entire, of the entire network. And the adjacencies are formed once we know this is all completed. Now, I want to add a couple of more notes as long as we're talking about a topology table here. We need to understand that every router, you see them here, A, B, C, and D, are going to have the exact same topology table within a specific area. That's one rule of topology tables. Another is going to be that when we want to update these different topology tables through here, we're going to use those link state advertisements we talked about earlier. In other words, the form of communication between these devices. And the cool thing about link state advertisements is it's not a broadcast type of medium. It's multicast, meaning that any router that has been enabled with OSPF is going to be listening to that specific multicast and is going to be available or ready for these LSAs to come in. But those people that aren't listening under that specific multicast don't have to bother with this. So it's going to save bandwidth over that broadcast type of information share, right? Well, here we go. Like we said, we're up to this topology table. We got a great snapshot of the entire network. But really, at this point, I don't have a specific path leaving these routers to different networks. I haven't populated a route table, which is what we most commonly see when we talk about distance vector protocols as the only table there, right? Well, here we go. We're going to make that jump for you. We've got this snapshot here, and it's a listing of all possible routes, not just the best route within a specific network, because it's going to be, again, that snapshot of the whole thing. And so we want to come up with the routing table, which is going to list the best route for our specific entry, specific router getting to another place. So what happens is we take this topology database, and we're going to run an algorithm on it. It's called the SPF algorithm. What a coincidence, right? Shortest path first algorithm. Another name it's going to be known by is the Dijkstra algorithm. So if you hear either one, it's exactly the same thing. And essentially, they're going to take all these possible routes and come up again with the best route. Well, as you can see, the best route for this router to different places in the network is going to be different than possibly the best route for this router, and then the best route for this router, because you can see that, you know, you can have topologies where there's a mesh here. You can have topologies where there's redundant links to different places. So every one of these routers is going to run this SPF algorithm on their own to produce a routing table. So this is what switched. When we talk about distance vector routing protocols, we understand that here trading information, trading complete routing tables all the time between all these routers is intensive, and it's going to eat up your bandwidth. Well, we're saving bandwidth when we talk about OSPF, but there is one area where we're going to use a lot of resource too, and that's going to be on the CPU. The processors of these individual routers are responsible for figuring out their own best paths and doing that through the SPF algorithm. So just know that you'll save on bandwidth, but you're going to need higher end CPUs when you run an OSPF within your given network. Now, up to this point, we've covered terms, we've covered the process and tables involved in creating a specific area made up of many routers in an OSPF type of network, right, as far as a routing protocol. But now we need to go beyond that area. The reason is, when we talk about OSPF, one of its great strengths is that it is not limited in size like you're going to find with other routing protocols. As an example, when we talk about RIP version 1, you're going to be limited by hop count, right? Well, guess what? You don't have that limitation when you're talking about OSPF because you can build multiple areas. Remember, we talked about an area already as a group of routers participating in a same area type of ID here, forming adjacencies, having a designated router within that group, all of that type of stuff. But we also have the ability to go and form into different areas. And we're going to do that via what's known as an area border router. So responsibility here is that they are going to have to participate within two different areas as far as the election on the designated router, as far as forming adjacencies and neighbors, as we said before. And so their tables are going to include information from both of these different areas. And that router is going to exist just like this. The difference between an area border router and any other router out there running OSPF is found in its interfaces. So if we have an interface here on this router and an interface here, and then again that subnet cloud on each end, and then a collection of other routers that exist within that network, same thing's going to be over here, then what you have that's unique here with the area border router is that it has interfaces that are in multiple areas. Just by that, just by definition, it says, okay, you're an area border router just because of the way you configured your interfaces. And this router over here, who has all interfaces within one area, it just says, you know what, you're a regular area router just because all of your interfaces are in one specific area. Let's say this is area 0, this is area 1. And we can grow that and include other areas as well, as long as we have these area border routers, right? And that's what's going to branch us off there. And the advantage of this is that when we have changes happen within our network, we can isolate them to areas, and because we know that a change here on this link doesn't really affect this route over here, the way OSPF works is it's going to come to a faster convergence by fixing the area right here, fixing the information it needs to, passing information if it does need to, and if it doesn't, knowing that it doesn't, and have a faster convergence. All right, so those are area border routers. We understand that they have multiple interfaces in different areas, and then we discussed the regular area here. So now the last thing we've got to define to bring all these terms together is the configuration commands. And luckily within OSPF, as far as required commands, there's only 2, and we're going to cover them here. Notice that I am in the global configuration mode, and that obviously I am in configuration mode, and you're going to see that this is familiar to you because when we activate other routing protocols, we do it in a similar fashion, router and in space, whatever the routing protocol is. But in this case, we're going to provide something here that is known as a process number. We've identified or provided autonomous system numbers and different things before, but in OSPF, called a process number, and it's simply an identifier so that we can have these different routers functioning within the same community, right? There are rules that govern this process number, but are beyond the scope of the CCNA at this point. We'll cover that in CCNP. All right, and then the second command that you need, as your prompt changes, because now you're in router OSPF, config-router, you simply need to identify the networks. Now, this network command is a bit more in-depth than what we've seen in the past with our distance vector routing protocols. So first I'm going to give you the common ground. We're going to have the word network, and then after that what you're going to provide is a specific network number. And this network number, just like other routing protocols, is going to be used to identify which interfaces within a router are going to participate in OSPF in this case, because we're talking about router OSPF. So let me do this. I'm going to say that this network hanging off of here is 192.168.1.0. I'm going to have 192.168.2.0. Each of these having a 24-bit mask, 192.168.3.0. And then the last one over here is 192.168, I'll make that a 1, .20.0, okay? Each of these interfaces on this router, respective to that network, is going to be .1, So here 192.168.20.1 is this interface. 1.1 is here. 3.1 is here. 2.1 is here, okay? So here we go. We have that set up, and we understand that we're going to provide this network statement to say which of these interfaces is going to participate. I'm going to give you a couple examples. And we're going to do that with this network statement and then a wildcard mask. We've dealt with those before, and basically what they're telling you is information that is needed to match exactly is going to be identified by having a 0, so we need an exact match. And then anytime we have a 1 in the value, that means we simply don't care what that value is. It can be anything. That's the wild card, okay? So let me give you an example here. First of all, if we had network space, and then the network we defined was 192.168.0.0, with our wildcard mask being 0.0.255.255, try to take a look here and think which interfaces would participate in OSPF. If you have to, you can stop the video and then come back. All right, well, here we are. What it's going to do is it's going to identify that every interface that shares a 192.168.anything.anything is going to participate. So we can draw 3 check marks. 1, 2, 3. Essentially, it's saying this one interface is the only one that does not want to participate. So you see how this network command can be very powerful in using one statement to identify and delineate between exactly the interfaces you want to use. Let me give you another example here. What if I said 192.168.0.0, so we have that same network number, but here's where we're going to change it up a second. 0.0.31.255. Because it's a wildcard mask, what we're saying is we want to identify that these last values here, and it's going to be, remember our binary chart, 1, 2, 4, 8, 16. These values, 1, 2, 3, 4, 5 characters in this third octet, are going to be able to be anything that you want it to be. And what that does is it gives you a network range here of 192.168.0, draw this here, 0 through 31, right? And because that's true, you can go over here and you can say, well, this statement means that every one of these networks is going to be activated. But what if I just wanted .20? Well, then what I'd write is 192.168.20. I could write .0 because it's going to, with this mask, 0.0.0.255, incorporate that .1 that's here. Or I could have written .1 instead and be 0.0.0. Instead of the 255, 0. So there's many ways to write this, and you have to pay particular attention to it because it has a bearing, a great bearing, on your interfaces and how they're going to participate within OSPF. Now, we're not done because, you know, we've seen this within other routing protocols where this is as much of the command as you needed, but here they're going to add another piece, and that's going to be the word area, and then you're going to provide an area number. This is why we've had such a great discussion on areas. We're going to say that each of these routers, or I'm sorry, each of these interfaces are going to be in an area. So here where we decided that 1, 2, 3 interfaces are participating in OSPF, we could say that we want them all to be within area 0, and indeed they will be. And if we had a statement where it just identified 192.168.20.1, we could say we want this to be in area number 1. And you kind of see how if you did that, that's where you're going to have your area border router configured. So these are the prime configuration commands that you're going to need to start OSPF up, start it on a network, and get things participating. Obviously, there are other commands that are going to give you more granularity as far as how these interfaces are going to interact in that OSPF world. But again, beyond the scope of the CCNA, we really just want you to be very comfortable and confident in coming up here and configuring OSPF on a router and understanding what these commands mean and what effect they're going to have within your network. Now, these basic commands I have given you are in support of a specific type of environment that you're going to operate when you talk about OSPF, and that's going to be broadcast multi-access. Make that an E. Basically, we're talking about Ethernet here, and this is the type of configuration that you would take on. There are other types of environments, point-to-point, like serial lines, point-to-multipoint, or even the idea of a non-broadcast, where you'd say non here, multi-access. That would be frame relay. So just understand that in different environments, there are different configurations that you're going to have to perform in special types of configuration. So keep that in mind, and it's something beyond the scope of the NA, so we'll cover that within the NP. All right, so far within this nugget, or in this nugget, we started out talking about terms. We identified the term neighbor, adjacency, designated router. We understood what an LSA is and also how updates are working specific to OSPF. From there, we talked about the process of a new OSPF router participating in that OSPF network, how it first forms a neighbor, then adjacencies and what that means, then the designated router election, and so on. We got to the point that we had a topology table. We built a neighbor table and a topology table, not yet a routing table. So in this section, we talked about how we're going to use that SPF algorithm to get from a topology table, a view of all possible paths, into a view of the best possible paths with our routing table. And then we just talked about configuration commands. I hope this has been informative for you, and I'd like to thank you for viewing.